Hello there, welcome to the 10th webinar. In this webinar, we will talk a lot about Fourier transform, about feature extraction in speech recognition, and all of this good stuff. So let's start by talking about Fourier transform to say what is it actually. A Fourier transform is an algorithm that can be used a lot in a single processing and in NLP. And what it does, it converts any type of time functions, like audio file, into its made up frequencies. Let me repeat it again. A Fourier transform converts any type of time function into its made up frequencies. For example, if you have any experience with musical instruments, you it's kind of going to be familiar for you because um, a musical chord, it can be expressed in terms of volume and frequency of its made up notes. So it's very similar to that as well. For using Fourier transform, we will use SciPy. It's been already written for you. Also, we will use NumPy. We will use Matplotlib for visualization, pyplot as PLT, and also Matplotlib inline. And also we will use Librosa, which is for plotting the wave, and also Librosa wave, it's important, display. And also we will use IPython for actually showing the audio file. We'll go more into it in a little bit later. So let's say import IPython display as we will say IPD, which stands for IPython display. Okay, let's run this. Now let's load the audio file. I already provide the audio file in a directory of data. You can find it there. So let's import this audio file, and for importing it we use the Librosa, and we will say librosa.load, and inside this load we will specify the directory. We'll say data, and so the name of the file is english.wave. This file will return two things. The first one is audio time series, or X. The second thing that it will return is sampling rate. So it will return first the audio time series and then sampling rate. Okay, now the audio file has been loaded. Now let's visualize it. At the very start, we want to specify the figure size that we want. And in here, more specifically, we want to have a 15 and 5. Now we want to do two things. First, display and visualize this audio signal that we have. A second thing that we want to also show its audio itself. So we will say Librosa.display that we imported here dot wave plot. And inside this, at the start, we have to specify the audio time series, which is this X. The second thing, we have to specify the sampling rate. Oops. Sampling rate. And the third thing, you can specify the alpha, which we will use 80%. And as I said, we also want to have something that when we click on it, we can hear the audio file, which will use this IPython display. And it has a, we say audio. And again, in here we'll specify the audio time series and also the sampling rate. Sampling rate, SR. Okay, now if you hear to it, let's hear to it. Okay, now this is the, we can play it, and also this is the its visualization of its signals. So now that we have loaded and also visualized this audio file, the next thing that we want to do is to compute its Fourier transform. And SciPy already take care of that for you, so the only thing that you have to say is SciPy dot fft, and we will just put this audio time series, which is x. Okay, it might take a while. Okay, while it's computing, after the computing is finished, we want to get the magnitude of computed Fourier transform, which for getting the magnitude, you only need to get the absolute of this value, which we will use numpy. We will say absolute x, and we will call this x mag, which stands for magnitude. So here it is. Then after getting this magnitude of x, we want to get the frequency variable. So what is frequency variable? For this, we will want to have an array. Oops. Okay, we want to have an array. We will use a len space that it starts from 0 and it will end from this sampling rate that we computed here, and we want to have a total of this x magnitude. So we are going to have an array. It starts with 0 and it will end with the sampling rate and with the total amount of this magnitude. We call this f, or frequency variable. Now let's actually plot this. We will, at the very start, we will define the figure size that we want, fixed size, and again we want to have a 13.5. Now let's plot it. So for plotting, we want the magnitude of a spectrum, which will use this frequency variable at the very start. Then we will use this x magnitude. Also, let's give a label to the x with frequency hertz. Also, want to show it. Okay, now we visualize this magnitude spectrum. It's very zoom out. Let's also zoom in this very specific part, so we can have a better understanding it. And more specifically, we will only let's visualize only until this 5,000. So let's say again plt dot figure fig size, which is equal to 13.5. We will plot first the frequency variable, but until 5,000, and also x magnitude until 5,000 again. We want to say that the x label is our frequency hertz, and let's show it. So this is the magnitude spectrum, but in more zoom, this area more specifically, so you can have a better understanding of this. So if you look at it, we convert this audio into this. This is the Fourier transform of this audio. Okay, very great. Now you have a very great understanding of Fourier transform. Now let's move to the next topic, which is about feature extraction and more specifically in the speech recognition. So what is feature extraction? Feature extraction is when we have an audio file, it's been loaded, and we want to extract some specific type of feature from that audio before we putting it in our neural networks. For example, if you want to classify the instruments based on their timbre, then you want to extract the features that is related to timbre and not pitch. On the other hand, if you want to classify the instrument by their pitch, then you will select some specific type of feature extraction that it will get the features that is related to pitch and not anything else. So for selecting your feature extraction, it's very important to choose something that is related to the problem you're trying to solve. So before we try some different type of feature extraction, let's start by importing our libraries and also importing the audio files. Again, like the previous time, we're gonna import the Liberosa and also Liberosa display. We're gonna import IPython display, and we will say we'll use IPD. Let's import NumPy, import SciPy, import matplotlib.pyplot. Also, let's say matplotlib inline. Okay, so for loading the dataset, we will say just X and SR, which X stands for audio time series, and also SR stands for sampling rate. You will say liberosa.load. We will specify the file, which the file is in a data directory, and the name of the file is english.wave. And let's also visualize it. We will say plt.figure fixed size equal to, let's say, 15.5. And now let's show the actual wave, the actual audio. We will say liberosa.display.waveplot. And at the very start, we will specify the audio time series, which is X. And also we'll specify the sampling rate. And also alpha, we'll say 80%. And also let's show the actual audio so you can actually play it. We will use IPython display for it. We'll say audio X, and also as a rate we will define sampling rate. Okay, here you go. This is our audio file, and all this is our its visualization. Okay, now let's talk about the first feature extraction that you're going to learn. It is called short-time Fourier transform, or on the other hand, we can also call it STFT. So you might say to yourself, what's the difference between this short-time Fourier transform and this Fourier transform that we learned in here? Well, this Fourier transform usually, and more specifically, let me show you to you. This Fourier transform usually produces a one-dimensional vector of numbers, and usually this, after computing this, the output is used to calculate two-dimensional vector of two-dimensional matrix of frequency magnitude versus frequency. And the same thing that we did here. So we don't usually use this alone because it only produces 1D dimension. And also this is usually represented as a 2-dimensional graph like this. So, and also this Fourier transform, we can use this when we want to understand the frequency spectrum of a signal. And on the other hand, this short time Fourier transform produces a 2D, two-dimensional matrix of frequency versus time. And this SDFT is usually used when we want to know at one time a particular frequency even happen in that signal. So that being said, let's start by computing this SDFT. And before computing it, we need to define two variables. The first one is called hop length, and hop length. The second one is called NFFT. So this hop length, it means that is the frame increment, which we can define a number around 512, and NFFT is the size of our FFT, which this can be something around 2048. After having these two, we can compute our short time Fourier transform by saying like liberosa dot st ft. At the start, we will put a x on it. This is the same x that we got our audio file. Let's make it capital X. Then we will define our number of the size of our FFT, and then we will define our hop length. Great. Now we have computed our SDFT. Now also let's convert this hop length and also frame size to its unit of seconds. And how we do it, how we are going to convert this to a unit of second, and also how convert this to a unit of second. Let's start by this hop length. So what we want to do first, we want to convert this to float number. So we just write float hop length. Then we will divide this to our SR here. Now we are going to have units of second. Let's just print it. This is our units of second of hop length. Now let's do also same thing for our NFT float. For our NFFT, we'll say FFT or SR. Great. Now let's also get the shape of this X, which is the output of this SDFT. Print X.shape. So what does this shape represent? The first one is our frequency beams, and the second one is the number of frames in our time. So that's how short you can actually start compute the short-term Fourier transform. Okay, now let's compute our spectrogram. So what is a spectrogram? A spectrogram is just the intensity of frequency over time. And the way we will compute it is just to take the square magnitude of this short-term Fourier transform. So what do I mean by that? How we can do this? Let's actually code along with it. We will call this S, stands for spectrogram. We will use the Liberoso library, and we will use something called amplitude to dB scaled spectrogram, which inside of it we only have to put the absolute value of this SDFT. So let's put absolute value of this X. So now we have computed our spectrogram, and let's now visualize it. Let's see how it actually looks. So plt.figure, for first define the size we want, fixed size, let's say 15.5, and also let's define a CMap. Let's define hot. And now for showing this spectrogram, again we have to use Libresso and something called display that we have imported, and spect show. So at the very start we have to put this spectrogram that we have computed. Then we have to define SR, that again we have it here, SR. And then we have to define the hop length. Again, we defined it here. And we can also define the x-axis. This is not necessary, but it's just for visualization. Our x-axis is time, and y-axis is going to be linear. Let me see what went I wrong. Now let's just define a color bar too. Color bar with the format. Okay, I forgot to delete this. Okay, now this is our spectrogram. Now we have visualized. Now after doing this feature extraction, this is very great for your speech recognition. You will use this spectrogram on your audios, and after doing this you can put this into your neural network and you will reach a very high result. Okay, now let's go to the next type of feature extraction that we are going to learn, and it is called MEL spectrogram. So let's start by computing it. However, before actually start coding the MEL spectrogram, we have to know two variables already. The first one is called hop length, which hop length is the frame increment. We will say something like 256. And another variable that we have to know is called NFFT, which is the size of our FFT. And we can define something like 1496. So let's call our MEL spectrogram big S. Again, we will use Libresso feature MEL spectrogram. And we put our X, which is our audio file. We put our SR. We will put our NFFT is equal to NFFT. Also, we will say hop length is equal to hop length. So now we have computed our MEL spectrogram. And in here I wrote a very long comment. So we actually, before using this, we need to convert this convert the power to dB units. And again, Libresso has a method called power to dB units. We will use the absolute number of this S, and we can call this log S. And now let's visualize this logos. Let's see how it looks. At the start, let's define the figure size, which we can have something like 15.5. Let's define the CMAP. Let's say hot. Now for visualization, again, we have to use Liberaso. We cannot use the matplotlib. Use Liberaso display spectrum. We will use this logos here. Then we will say SR equal to SR. Hop length is equal to hop length. And also we can define our x-axis, which in this case our x-axis is again time, and our y-axis is mil, this is mil spectrum. Okay, now also let's define the color bar. Save format. To dB. Okay, this is our mil spectrogram. Have you seen any changes? If you notice in mil spectrogram, we somehow don't have this extra parts. It's like we zoomed a little bit somehow. Okay, now let's go to the next feature extraction, which is called constant Q transform, or CQT. Before computing the CQT, we have to have our F min, which is minimum frequency. For getting the minimum frequency, again we will use the Liberosa, and in here we want to get the frequency of the MIDI notes, and there's a method, it's called MIDI to Hertz, which Hertz again is for the frequency. We will say 36. We will define our CQT, which we will again use Liberosa and CQT method. At the very start, we will put our audio file, then SR, then minimum frequency, then number of pins, we can say something like 72. And again, like before, like we did in our mel spectrogram, we have to get the log. So we call this log C, Liberosa, and we want to convert the amplitude to dB units. And we will use the absolute value of our CQT. Great, now we have computed our CQT, and we can take a look at our CQT. So let's at the start define the figure size. Again, we can say something like 15.5. For visualization, again, we will use Liberosa, display, spectrum. Here we use at the start log C, and then we will say SR, and we will define our x-axis, which again is time, and also our y-axis is CQT note. Minimum, we have to also define the minimum frequency, and also we can define the CMAP here as well. We can say cool word. Now also let's define the color bar, format, beauty. Great. Now you can actually just, if you take a look at it, you can see how different these different feature extraction are. So lastly, let's go to the very last feature extraction that we're going to talk, and it is called male frequency cepstral coefficient, or MFCC. So let's start by loading another audio file. Again, it will return X and also SR, sampling rate, which we will use liberoso.load. We'll define the path for it, which is inside data, and inside data the file name is something like this. Let's also display it with liberoso and also with IPython. So liberoso display wave plots, X and sampling rates. We will use IPython display. Again, we will put X and also sampling rate. Okay, maybe the file is a little bit longer. It's around 1 minute. That's why it took a little bit longer. So after getting our audio, now let's start computing the MFCC. We'll call it MFCCs. And liberoso feature MFCC, as simple as that. And we put our X and also sampling rate. We can also see the shape, which is going to be 2-dimension. Okay, great. Now let's visualize our MFCC. Now we have computed it with just a single line of code. Now let's also visualize it to see how it looks. Liberoso, display, spectral. Also sampling rate, x-axis is time. So this is our MFCC. Let's also try again, visualize the MFCC again, but before that let's scale it. So we will scale it in a way that each coefficient dimension has a zero mean and unit variance. And how we do it is just using a scalar. Let's import it here. Import scalar. We'll say MFCCS again, scalar.preprocessing.scale. And inside we will put our MFCCS, and also we want to apply it to axis 1. If you want, you can actually also look at its mean, and also let's take a look at that, and also variance. We'll say MFCCS dot mean axis 1 and also variance. Okay, great. Now let's, after we scale it, let's also visualize it again. Let's see what's going to be any difference. We'll use liberoso, display, spectral, MFCCS, SR, and also x-axis, which is time. See how different it is after doing scaling. So now you learn few of the feature extraction here. They were all important, and depending on the problem you're trying to solve, you might take a different feature extraction. And if you're interested, I'm really highly recommend you to go inside this page and literally learn everything. They have a great resources, great resources. And also there is two notes included here: introduction to voice user interface and also automatic speech recognition, which all of these notes are taken from your Udacity videos. I just wrote them down for you. So if you don't have any time for taking notes, I hope this can be useful for you. Before finishing this webinar, I want to introduce you to a software which you do not need to actually code all of this. You can just play around with this software, see all of these feature extraction. The name of that software is called Sonic Visualizer. And we will now go download it and we'll just take a look at it. So this is the first page of the Sonic Visualizer. You will go here, and depending on what operating system you will choose, use the primary one. And let's wait until it gets downloaded, then we will install it and we will see how it actually works. Okay, it got downloaded. Now let's install it. Okay, now it got loaded. Now let's load the same file that we have used inside here, and let's also check it out its feature extraction. Okay, the file is here. It's imported. Yes. Okay, as you can see, this is the visualization of our audio. Is quite small because it was very short. So let's say you want to check out the spectrogram in the software. The way you will do it, you will go to this pane and you will add spectrogram, and you can see actually how its spectrogram looks. It's a very good idea to actually play around with this. You will get quite familiar how it works. You can use another stuff, play with it. Let's see and see how it works. I hope you enjoyed this webinar as much as I did, and see you next webinar. Thank you.